Please welcome Professor Chris Lintott.
Evening, everybody. Thank you very much for being here. I thought this was a good subject for a cold January day, and I'm delighted to see that so many of you agree. This has been the most difficult lecture I've written of my tenure at Gresham so far, because the sun is so familiar to all of us. Wherever humankind has gone, wherever we've been in the world, or indeed in the solar system, we have the sun as our constant presence. And so it's a subject that you perhaps feel you know all about. This is a gratuitous sunset photo taken on Mars by one of the Mars rovers from Spirit, the robot geologist that explored the red planet on May the 19th, 2005, showing sunset on the planet. But it's that familiar scene rendered Earth-like by the presence of our friendly neighborhood star. It gives us the sky that we're used to. The blue color in this image is pretty close to what you would have seen if you were sitting on Mars next to the rover. Do take your own oxygen, of course. And it's striking how universal an understanding of the sun as an important and friendly presence is. Even in kids' drawings, this masterpiece by my nephew Finn, for example, shows a dramatic scene. He calls it the end of the dinosaurs. I think a volcano is involved. But despite the devastation on Earth, in the top left, a nice friendly yellow disk with rays coming out of it, how we all think about the sun, though I guess sometimes it has sunglasses on as well. Fred Hoyle, the great cosmologist and the person who taught us how many of the stars in the universe shine, once started a lecture on stellar, not solar, but stellar structure in Cambridge by noting that stars are simple. And a heckler from the back of the room said, "If you were that far away, you'd look simple too, Fred." And one of the problems that I have approaching the sun as an astrophysicist is that it's close enough that we can see that it's complicated. When stars are distant, when they're just a point of light in the night sky, then it's easy to think of them as simple. But when we can see the sun close up, we get a long way from the picture that we're used to drawing as kids. The lecture is particularly timely because of the adventures of a small space probe shown here in this artist's impression, the Parker Solar Probe, which has just fulfilled an ambition that goes back to the dawning of the space age. One of the three tasks that were set to NASA when it was set up in the late 1950s was to send a craft close to the sun to understand the processes that drive our star. This was so complicated that it's only been achieved in the last few weeks. The Parker Solar Probe flew closer than any other object ever has to the solar surface. If the sun and the Earth were a meter apart, then the closest approach would have been about 4 centimeters. And the probe, as it passed just 3.8 million miles above the visible surface of the star, was moving at 430,000 miles per hour, making it the fastest human-made object ever. It's a remarkable technological achievement. The temperature on the front of the probe was about 1,000 degrees centigrade, and the reason it took NASA 70 years to get to this technology was that a heat shield needed to be developed so that the instruments work at pretty much room temperature, despite the presence of the sun just on the other side of them. So this lecture includes some of the latest results from Parker, but also from a whole suite of missions which carpet the solar system and which help us understand what's happening on our nearest star. There are many examples here, and I won't go through them all, but what I really want to point out is that pretty much any spacecraft in operation is doing some sort of solar sensing. There's an example given here in the bottom right of the latest Mars rover, Curiosity, which has a radiation instrument to monitor the effect of solar weather on the red planet. And I'll come back right at the end of the talk to the contributions of the Voyager probes, initially launched to explore the giant planets of the solar system, but now out in interstellar space, giving us the other end of the story from Parker. This is the only time, I suspect, in our lifetimes where we'll be receiving data both from a spacecraft that's skimming through the atmosphere of the sun and from spacecraft that are out on the edge of the solar system. And combining those two things tells us a story that affects us sitting in the middle on Earth. The other spacecraft I want to make sure that I mention right up at the top is a European contribution to this fleet. It's a spacecraft called Solar Orbiter, which sits a little further out than Parker. It's on a 6-month elliptical orbit, so it swings closer and further away from the sun. And its role is essentially to monitor the whole disk. So this is a few months' worth, actually about a year's worth of Solar Orbiter images in the ultraviolet that shows an active sun with details that we'll get into. And the blue flashes here are flares, material that's flung off out into the solar system. And you can see the detail in these images when combined with the instruments from Parker's remarkable passage close to the sun are giving us a new picture of this star. But we should go back to basics. We should talk about the things that everyone knows about the sun. And I have to say, I started trying to write this lecture right at the end of last year, as I was sort of reaching Christmas burnout around the time when term had finished, and I was pretty overwhelmed. And I sat with a piece of paper for an hour trying to think about what I wanted to tell you about the sun. And maybe I'll just show you those notes, because I think they capture where I got to. You see, this is what people know about the sun. So it is true that the sun is massive. I get paid for this lecture. It is true that the sun is massive. Now, how we know that is interesting. It's calculated by an understanding of orbital mechanics, of watching the planets go round the sun, enables you to calculate this number, the mass of the sun. But you do need to know the distance to the sun. And that was first calculated with precision in the 18th century when astronomers watched the transit of Venus, when they watched the planet Venus pass in front of the sun from different places on the Earth and used parallax, the difference in timings of that event from different places, to work out a distance, plug that into the maths via a method originally suggested by Edmund Halley and others, and you end up with the idea that the sun weighs about 333,000 times the mass of the Earth. So that's about 2 times 10 to the 30, so 1,000 billion kilograms. It's massive. Tick, first thing achieved. It's also big, I guess, I should say that. It's about 1.3 million Earths by volume and about 109 across the front. Hot is rather more controversial, which sounds ridiculous. Surely the one thing we know is that the sun is hot, but the great William Herschel, the greatest English observer of all time, the discoverer of Uranus, in the 18th century was a proponent of the idea that the sun was cold. In fact, he described it as a cool, dark, solid globe, clothed in luxuriant vegetation, doubtlessly richly stored with inhabitants, so he thought people lived on the sun, and he said, look, if the argument's this, so he's actually got this model, so here we go. So you have a dark Earth-like globe, then you have a planetary clouds which block our view of what are presumably cities and civilizations on the surface of the sun, and then there's a luminous shell above that which we see. And this sounds ridiculous, but his argument was, look, if it was just light that caused heat, if the fact that this was luminous meant it was hot, then surely the tops of mountains which are closer to the sun would be warm rather than snow-covered. And so he argued that you need what he called a calorific medium, something on the ground that converts light to heat. And in the absence of that, surely people could live on the sun. Now, I'm here to declare that this is actually our modern... No, not really. We no longer believe that the sun is inhabited. We know that it's hot, and people quickly realized in the 18th century that, indeed, the light from the sun indicates that it's hot, about 6,000 degrees on the visible surface. But that opened up the argument of where the source of the energy that the sun provides is coming from. It was a problem that troubled a large number of physicists, many of which looked slightly like walruses. This is Kelvin and this is Helmholtz, two of the people engaged in this. Kelvin, probably the great 19th century physicist. They argued that the sun really had to get its source of energy internally. That what was happening was that material that made up the sun, either primordial material that had been assembled somehow into this star, or material that was still raining down onto the sun, comets, meteors, and so on, that the contraction of that material, squeezed under gravity, would release heat. Kelvin said that some form of this theory is certainly the true and complete explanation of solar heat, and this can scarcely be doubted when the following reasons are considered. One, no other natural explanation can be conceived. All right, well, that's cheating. Two, the chemical theory, the idea that the sun is made of coal or something like that, is quite insufficient because the most energetic chemical action that we know taking place between substances amounting to the whole sun's mass, so this is if the sun was made of coal or something like that, would generate 3,000 years heat. And they knew that the Earth was older than 3,000 years. And he goes on and says, there's no difficulty in counting for 20 million years worth of heat by the meteoric theory, by this collapse. And you can actually work out, we know the mass of the sun, you can work out what's called the Kelvin-Helmholtz timescale, you can work out how long that body would take to collapse, and you get a value in sort of tens of millions of years. So you can explain a solar system that's tens of millions of years old just by having things collapse. And you can extend it a bit by throwing more stuff in, and indeed today, using satellites like SOHO, with the sun's disk blocked out here, we see comets plunging into the sun. That's a comet on the right there, and about 4,000 or 5,000 of these things have been seen in the last 20 years. So stuff does fall in. You still can't quite beat a few tens of millions of years. And this is a problem, because of observations made by people like geologist James Hutton of places like this. This is Sicker Point in Scotland. This is a place where two different types of rock rub up against each other. In fact, you can see in this sketch made in 1788 from James Hall the crucial observation. You've got these vertical rocks. These are grey wacke sandstone, very suitable for growing Sauvignon Blanc on, but probably not in Scotland. But importantly, deposited over many millions of years, possibly at the base of an ocean. We now know they're about 435 million years old. But they're topped by these rocks with a different angle of spread. Those are the red ones on the top there. This is an old red sandstone. It's 360 million years ago old. And in between, there's 65 million years of missing history. And Hutton knew that here and in other places, he was looking at two slow processes with an unknown gap in between them. And he used things like this to argue for the concept of deep time. Though he wouldn't have known the numbers that I told you, he realized that the Earth had to be hundreds of millions or even billions of years old. And so a theory of the sun's heat, which could only account for a sun that maybe was 20 or 30 million years ago, was incompatible with geology, with a growing understanding of how old the Earth was. This was not a view accepted by Kelvin, and a controversy about whether the Earth truly was old or whether the sun needed a different power source rumbled on for most of the 19th century until it was realized that there was another potential source. Radioactivity was discovered in the lab. Materials that when they break down under nuclear fission emit heat were discovered, so if you make the sun of those, you can have a long-lived radioactive sun. So this means the crucial question becomes, what is the sun made of? And unbelievably, we can actually measure that directly. This is a modern picture of the solar spectrum, of the light of the sun split into its constituent wavelengths. You can see immediately two features. One is that there's a rainbow, and here I've wrapped the rainbow round so that it's not just one long strip, but you go from top to bottom. But second, that there are these dark patches, and both of these things are important. Now, the solar rainbow was known since Newton's time. Newton did experiments like that described in this rather charming diagram that showed in 1672 that if you passed light through a prism, it splits into a rainbow. What appears to be bright white sunlight is actually made up of all the colors combined. But in the early 19th century, a German scientist called Fraunhofer made the discovery of these dark lines. They're still called Fraunhofer lines. Fraunhofer, by the way, if you ever get a chance, read up on his biography. It's an extraordinary life. He was orphaned at the age of 11, apprenticed to a glassmaker who treated him appallingly, and then the shop that he was working in collapsed, and the young Fraunhofer happened to be rescued by a passing prince who got talking to him and funded his scientific education as a result, forcing his employer to provide both books and time to study, thus leading to one of the great scientific careers, which was then cut short at the age of 39 because of exposure to heavy metals from his glassmaking. But in between, he discovered these dark lines in the solar spectrum. And the explanation for these we now know, since Kirchhoff and Bunsen and others in the 19th century, is that these are the fingerprints of different elements in the solar spectrum. So the way this works is you have a source of light, of all colors of light. Let's just take it as read that the sun's that for now. That would produce a continuous rainbow, like in the bottom left. If you have a cloud of gas, emission from gaseous molecules would produce a series of bright lines, and the position of these lines tells you which elements exist in the gas. This is a process to do with the capture and escape of electrons in different species that correspond to different energies. If you're looking at a cloud of gas in front of a bright source, then you end up with this absorption spectra, with these dark lines, as we see in the sun. So what we're seeing in Fraunhofer's observations is the effect of the solar atmosphere on the light that's coming from the bright surface of the sun. A race was on to try and identify which lines corresponded to which elements. Most famously, people like Norman Lockyer, working in first Kensington and then in Devon, discovered that some of these lines appeared to belong to a new element, to helium, named after Helios, the sun god, but also that the sun seemed almost overwhelmingly to be made of hydrogen. And so our radioactive theory, the idea that you could power the sun with heavy elements, disappears. There isn't enough heavy stuff in the uranium, or not much uranium, etc., in the sun to provide a heat source. And so this mystery of what the sun's power source actually was persisted into the 20th century. Now, I should say it was understood that the sun was hot. We've established that already. And that makes things slightly simpler when we're thinking about the structure of the sun. Now, I can quote, for example, contemporary philosophers, they might be giants, who sang, as many of you will know, that the sun is a mass of incandescent gas. And this is not true. The sun is at a high enough temperature that its atoms have lost their electrons. And so the sun exists not as a gas, but as a plasma, where you have atomic nuclei and then free-floating electrons. And to be fair to the band They Might Be Giants, I should point out they have re-recorded, I'm delighted to have discovered in preparing this lecture, a new version of their song, which begins, "The sun is a miasma of incandescent plasma," which I'm sure we can all agree is an improvement. So, we have a hot sun made of atomic nuclei with a sea of electrons. In 1920, Eddington, who we met in last time's black hole lecture, realized that nuclear fusion could be the answer. That if you took 4 hydrogen atoms and fused them together, you can produce a single helium atom. And it was newly discovered in the 1920s that the weight of one helium atom is a tiny percentage smaller than the weight of 4 hydrogen atoms. And because of that difference, when you fuse 4 hydrogen atoms together to form 1 helium, you get, via E equals mc squared, Einstein's great equation, a release of energy. And so Eddington realized that the sun could be burning hydrogen to helium. And indeed, that's what's happening at its core at temperatures of millions of degrees. There's a cycle of reactions happening, the most common of which is known as the proton-proton-1 cycle, which is shown here. You take 2 protons, 2 hydrogen nuclei, they merge, they produce a deuterium nucleus with 1 proton and 1 neutron. That then merges with another proton. You form a helium nucleus with 2 protons and a neutron, and then you merge two of those together and you get your final stable form of helium and two hydrogens. This is not a fast process. It's very sensitive to temperature, actually proportional to T to the 12, so a small change in temperature will make a big difference. And the average proton in the center of the sun will hang around for about 9 billion years before it takes part in this reaction. It's that first step that's limiting, and as a result, the lifetime of the sun is of order 8 to 10 billion years. Once you form your deuterium, that goes fast. That will merge within about a second, and then about 400 years for the helium-3 to form stable helium-4. And there are other more complicated reactions that are going on as well. I should say, by the way, that it's been argued by my predecessor in this chair, John Barrow, and others, that we're lucky that the universe does this. You can imagine a world in which helium-2, in other words, a nucleus of just 2 protons, is stable. So that you could have a much simpler process by which 2 protons come together directly, form helium-2, and the process stops. In our universe, that nucleus isn't stable, and it would split back out into 2 protons. But if it were, then stars would very quickly produce a lot of helium-2, and you'd burn through their fuel almost instantly in the matter of a few million years. And that would mean that there'd be no long-lived stars, and hence presumably no planets with life on in the universe. So this is often used as an argument that we live in a universe where we should pay attention to the anthropic principle, the idea that the universe is the way it is because we're here to see it. We don't live in that universe, we have this proton-proton cycle, and it would be nice to know that this complicated chain of reactions is actually what's going on. And luckily we get some direct evidence for this. One of the byproducts of that first reaction, the combination of 2 protons, is a small particle called a neutrino. Now neutrinos don't interact with their surroundings very easily at all. John Updike, the poet, wrote a poem about neutrinos, and he said, "The Earth is just a silly ball to them through which they simply pass." They also simply pass through the rest of the structure of the sun. They escape from the sun pretty quickly, and seen here is the Super Kamiokande detector in Japan, a giant tank made of water surrounded by photomultiplier tubes with a bunch of physicists in a rubber boat slowly inspecting their instrument in this case, which can detect the passage of these neutrinos. And we now know that we get the predicted number of neutrinos from the sun as we'd expect from this proton-proton cycle. There was a controversy for a while because we didn't see enough, but we now know that neutrinos can undergo a change on the way from the sun. If we take that into account, we can see direct evidence that the proton-proton cycle is happening. As important is the fact that those early reactions, and indeed several other steps, produce light at the center of the sun. And that radiation spreads out from the center of the star. But one of the more astounding facts is that we don't see it instantly. We're used to thinking of light moving quickly. But if you're outside today, the sunlight that you were enjoying left the center of the sun about 170,000 years ago, about the same time that the first Homo sapiens were congratulating themselves for inventing clothing, to give you a scale. What happens is, because of the density of the sun, any photon emitted at the core will quickly encounter another proton, be absorbed, and then re-emitted. And so they bounce around in essentially a random walk. This is one simulated example of the path taken by a photon in escaping the sun. So until they reach the surface, they disappear. They take this very long and convoluted process. They then take 8 minutes to get to us from the sun traveling through free space. The picture's complicated again. We actually have a core, a radiative zone where these photons are able to move outwards, and then there's a convective zone at the top, an area where there are large circulations of material rising and falling in the outer layers of the sun, rather like the circulation of Earth in the great air currents that we see in our atmosphere. We know about this structure because colleagues have made a detailed study of the vibrations of the surface of the sun, a science called helioseismology. which seems to delight in wonderful names for experiments. There's GONG, the Global Oscillations Network Group. Trying quite hard there to make that work. And my favorite, our local helioseismologists, BISON, the Birmingham Solar Oscillations Network. And they've done an enormous amount of work, the equivalent of using earthquakes to understand the Earth's core. We look at vibrations on the surface of the sun to understand the internal structure. The core is mysterious. The rest of it has begun to make sense. So we have this surface, we have this continuous spectrum. It's an interesting problem, by the way, why the sun emits a broad brush spectrum, a continuous spectrum. I don't have time to talk about it, but when we look at that visible surface, that area from which photons escape, when we look in detail, then we see a remarkably complicated picture. This is an image from the Daniel K. Inouye Solar Telescope in Hawaii. Each cell that you see here is the size of Texas, and I'm going to take 10 minutes of observation, speed them up for you. And what you're seeing here is a dynamic surface of the sun. This isn't a computer simulation. These are real images from the largest telescope in the world that studies the sun. And what you can see is a changing pattern of what are known as granules, these cell-like structures which swell and shrink, which turn over and represent the upper surface of that convective zone, that region where material's bubbling up to the surface. If I play that again, you can see in between the granules, there are really fine scale structures. The smallest features in this image are only about 30 kilometers across, and those bright patches are going to turn out to be very important. But even here, with this first close-up image of the sun, we've come a long way from a bright yellow disk in the sky. We've reached a complicated and difficult place to explain. Let's zoom out a bit. Here's the sun as it was yesterday, seen by the Solar Dynamical Observatory, and this is an ultraviolet image, so you can see on the surface of the sun, bright patches here are hot, so there are areas of intense activity. We've got these strange streamers that are twisted around. There's this large dark region across the center, a cooler region on the surface of the sun. But if we step through different wavelengths of light, if we use different cameras, the picture changes. So you can see here, in the extreme ultraviolet, you can see that there is activity. That dark area has become a site of one large structure. We can see in this image there are filaments and prominences on the edge of the sun, large loops, each of which is big enough to contain the Earth. And in excited X-rays, we see that those areas where materials shooting up into the sun are extremely hot indeed, going up to a few million degrees. I recommend, by the way, the Solar Dynamic Observatory updates its images about 3 or 4 times a day, and I really recommend starting your day by seeing what the sun's doing. It's a nice way to feel part of the universe. You don't even need these fancy cameras. This is from SDO, again from yesterday, but this is a visible light image of the sun. And in some ways, this is the oldest sort of solar observing. What you can see here is the yellow disk that we're expecting, but there are also a couple of dark sunspot groups on the sun at the minute. And these have been observed from before telescopic times, when people occasionally were able to look at the sun through thick fog. Do not try and look at the sun directly. It's dangerous. You will blind yourself if you try and use optical aid to do that. But early telescopic observers, Galileo and Thomas Harriot, the first person in the UK, we think, to make scientific instruments, observations with a telescope, in 1610, spotted sunspots. I should say Thomas Harriot, if you don't know the Harriot story, he's great. He got hold of what he called a Dutch trunk, which turns out to have been a telescope. He drew the first map of the moon, and I was talking to somebody about him yesterday, and found out that he's credited with the introduction of the potato to the UK. So the first astronomer and the person who invented chips, he should be a national hero, I think. Anyway, I'm not going to show you these are Galileo's observations of sunspots. He did actually damage his eyes by making these, but this is a modern animation And what you can see is that over the course of several days, this is about a month's worth of observations of the sun made at about the same time each day, the spots move across the surface, and they also change and evolve as they do. So by watching sunspots like this, observers were able to deduce that the sun rotates, but it has a rotation period that depends on where you are. It's about 24 and a half days near the equator, about 36 days near the poles. So there's what we call a differential rotation. Remember, this isn't a solid body. It's a miasma of incandescent plasma. It is a rotating body of gas, if you prefer. So what's going on? What are these sunspots? Well, they're produced by the magnetic field of the sun. And we're used to the idea of magnetic fields. If you remember your geography at school, you'll know that we think of the Earth as having the kind of field that you associate with a bar magnet, with poles and then these looping field lines. And that's a pretty good first description of the solar field, except that the entire sun is rotating. And so that means that once every 8 months, the field lines get completely wrapped around the sun, doubling the strength of the field. And so you end up with a twisted magnetic field. There's also all that motion I told you about in the upper layers of the solar atmosphere. And that causes twisting in the field. And you can think of this as twisting up elastic bands. So you're storing energy within the magnetic field. And that stored energy, and its need to escape, creates a range of behavior, including sunspots. So here are some more examples from that telescope on Maui in Hawaii. They show the complexity of the quiet sun in the top right and the bottom left, where there are these dark threads visible. But the other images here are all sunspots. Here is a particularly lovely example. The dark region is cooler. Because it's cooler, light is escaping from the solar surface lower down. So this is a place where we're seeing down into the sun. You can see the dark umbra, the central shadow, surrounded by the brighter penumbra, which has these filaments. And on the left here, these are decaying sunspots. We're watching the end of one of these sunspots. This is a place where magnetic field lines are escaping out of the sun, and they're causing material to flow. Early observers realized that these sunspots and other markers of solar activity follow a cycle. Here's an annual survey of the state of the sun, running from 1996 to 2020, from the long-lived SOHO probe that the European Space Agency and NASA collaborated on. And what you can see is that we start off in 96 with a quiet sun, it becomes more active, it returns to being quiet, and then it repeats again. And there's a roughly 11-year cycle here. More remarkably, if you plot the positions of sunspots each day on a graph, you get what's called the butterfly diagram. So not only does activity come and go, it moves across the surface of the sun. You start each cycle with sunspots far from the equator. Over time, over the 11 years, they move closer to the center. And over time, then the sunspots of the next cycle will appear. So one can measure out your life in solar cycles. We count from the first cycle that was observed in 1755. We're currently in cycle 25. I guess I was born at the tail end of 20, went to school during cycle 21, university 22, and have been thinking about astronomy for most of cycle 23 and 24. But you can also see from this graph at the bottom here, and this is just the area of the sun that's covered with a sunspot, you see there are obviously longer-term trends here as well. That each cycle isn't the same. And it's possible that we've lived through a period of intense solar activity that's now fading. That we expect the current cycle, 24 was very puny, 25 is at its maximum now, but does not appear to be back to, say, the heights that we saw in the 50s or 60s. And it's possible we're entering a period where there'll be very little solar activity. Now, I should say that's not enough to allow us to get away with climate change. A change in temperature might be as much as a fraction of a degree because of this change, but it shows us that there's a complex long-term evolution of the sun going on, that each cycle affects its subsequent neighbors and so on. And the origins of this 11-year cycle are still being debated today. We actually think it's a 22-year cycle because the polarity, the north and south pole, flip in between each cycle. But we should continue on outwards. We reach the solar surface and sunspots. We can go further. We can look at the solar corona, its atmosphere, seen here during a total solar eclipse. During such an event, the moon blocks out the bright photosphere of the sun, and we're left with a momentary glimpse lasting just a few minutes of the pearly white corona of the sun. You can see here there's also a few prominences around on the right-hand side, those places where material's being thrown up above the solar surface, shown here in red. Now, if you haven't seen an eclipse, I want to pause the lecture briefly to recommend that you do. I couldn't think of a way to be persuasive other than to show you the effect of an eclipse. And so this is me about 3 minutes after I'd lived through totality in Farmersville, Ohio, back in April. Every time I try and tell people what an eclipse is like, what a total eclipse is like, and there are no words for it. I cried. It was beautiful. There were prominences. There's a prominence, a bright orange glow at the bottom of the sun. Beautiful corona, long streamers, a solar maximum corona, all of which makes sense scientifically, but my God, we're so lucky to live on a planet. There's more, and I had a Bloody Mary, but I sincerely recommend it. It's one of life's great experiences. The next time in the UK is September 2090. 2030. You can go to the Channel Islands in 2081, but if you do get a chance to travel, do get yourself into a total eclipse. Now, that reaction is one of the reasons I can't be a solar physicist, because solar physicists like to make their measurements of their corona during eclipses, and they've taught us, for example, that the shape of the corona changes. This is 1994's total eclipse versus 1980. 1994 was a solar minimum, very little solar activity. We've got these long streamers. 1980, a solar maximum, we have a much more symmetrical corona. So the atmosphere is responsive to what's happening underneath. Solar physicists are impatient. They don't like to wait for eclipses, and so people have used a variety of methods to try and study the corona the rest of the time. The early attempts involved putting telescopes on early sounding rockets, flying them under balloons, or in one of my favorite inventions, a thing called a rockoon, which is what happens when you put a rocket underneath a balloon and then wait to launch it until the time is right. The idea here was to catch the sun being active. So they would fly a high altitude balloon with a rocket, wait for the sun to do something interesting, and then blast the rocket into space to take quick observations, usually going straight through the balloon itself as well, causing all sorts of interesting landfall. Results from slightly MacGyverish experiments like this taught us that the corona is hot. It's actually hotter than the surface of the sun. It's millions of degrees. And we can study it now with coronagraphs. This is a satellite in space, SOHO, that's blocked out the sun so you can see the outer corona. But understanding how you resolve this paradox of an outer atmosphere that's hotter than the surface of the body that's heating it took a long while. It required specialized spacecraft, some of which sent back spectacular images. This is a video from the TRACE spacecraft, which was sent up to look at the corona and particularly how it relates to the surface of the sun. This is a video from 1998. We can zoom in and you can see the complexity of what's going on the surface here. These streamers link up from the surface of the sun into the atmosphere, and they must carry magnetic flux and material up into the corona. But the details, to the frustration of physicists, weren't available from images like this. They look fantastic. I had trace imagery as my computer background for a long time, but it's only when we got back to these images, taken in the last few years, that show those 30-kilometer size features that people could see what's going on. If you look, there are bright patches in between the cells, in between the granules. And those bright patches are places where material is connecting back up to the corona. So it's the structure of the sun in between these active regions that's heating up its outer atmosphere and maintaining a corona at millions of degrees. Now, that corona stretches out into space. It can have a dramatic effect on its surroundings. This is an image from a spacecraft called Stereo. Stereo was actually a mission with two probes, one which went ahead of the Earth and one which went behind the Earth and which looked back at the space between the sun, which is off to the right of this image near the grasshopper, and the left. And you can see in a movie over the course of one day, material flowing outwards from the corona. And the thing coming inwards is poor Comet Encke, a periodic comet, which you can see is disrupted. Its tail acts like a windsock in the face of this solar wind. And you can actually see somewhere about a third of the way through the video, the tail disconnects there and disappears out, carried out to the outer solar system. The comet perseveres bravely. On Earth, we experience an interaction with the sun when we see the northern lights. We had a couple of amazing displays last year. This is from October, taken just down the road from my home in Oxford, showing a beautiful display of the aurora caused by particles from the solar wind hitting our planet's atmosphere, being funneled by its magnetic field down to the upper atmosphere and exciting atoms in our atmosphere to glow. But understanding where that solar wind comes from is, again, a big problem. This is why solar physicists wanted to get as close to the sun as Parker did. For the first time, the Parker Solar Probe is flying close enough to the sun to be in the region where the particles that form this solar wind are accelerated. So we're actually studying the processes which speed up this wind that spreads out into the solar system. And sometimes we've been able to combine those results with more distant views. So this is a view of the sun from March in 2022. And at this time, Parker was close to the sun, so we had a sense of what was going on low down in the solar wind. The dotted line here represents the solar orbiter trajectory, so we got this view of what was happening down on the surface. And if you imagine being able to put together an instrument that's collecting and analyzing the particles that are flowing from the sun with this detailed view, you can see why scientists are now confident that we understand where the solar wind is coming from. It's from this complex and magnetic interaction around the active regions on the sun, not from the activity that we see itself, but from its effects on the rest of the sun. Solar activity can be more dramatic. This is the 1860 eclipse. This is a beautiful drawing of the corona, but it appears to me that the observer has dropped a cinnamon roll or something onto their telescope. This feature down in the bottom right, which appears in all contemporary descriptions of this one particular eclipse in 1860, is what we would call a coronal mass ejection. This is a modern version of that from Soho. And a CME is a mountain's worth of material shed quickly from the sun and sent flooding across the solar system. My friend Chris Scott, who studies the sun and its effects on our upper atmosphere, talks about it as a billion tons of matter moving at 1 million miles an hour across the solar system. And these things slam into our atmosphere and cause spectacular auroral displays. The most exciting of those came just a year before 1860 eclipse. It's known as the Carrington event, after the observer in the UK, in fact in Surrey. This is the rather wonderful Red Hill Observatory, a nice bucolic house with a dome stuck on the end, every astronomer's dream home. This is Richard Carrington, who made in 1859 a drawing on the 1st of September of this extremely large and complicated sunspot group on the surface of the sun. And Carrington noticed while he was observing that there was a flash of light that was brighter than anything he'd seen. And what he'd seen was one of these coronal mass ejections, we think, shooting up from this sunspot group. 24 hours later, magnetic observatories in Greenwich and elsewhere recorded a disturbance in the Earth's magnetic field, and an enormous auroral storm was seen more or less right across the planet. There's a wonderful description, for example, from a gold miner in Perth in Australia. Now, that's pretty close to the equator. We don't normally get the southern lights there, but the record records that a scene of almost unspeakable beauty presented itself. Lights of every imaginable colour issued from the southern heavens, with one colour fading away, only to give place to another, if possible more beautiful than the last. The streams mounting to the zenith, but always becoming a rich purple when reaching there. The rationalist and the pantheist saw nature in her most exquisite robes, recognizing the divine immanence, immutable law, cause and effect. The superstitious and the fanatical had dire forebodings and thought it a foreshadowing of Armageddon and final dissolution. This is the kind of scientific description we deserve, I think, for these kind of events. The point is, it was spectacular. There's a wonderful record of telegraph operators in the US discovering that they could operate their systems without any power source. They unplugged their batteries and found they could still communicate across the continent because of the electrical current provided by the Aurora. Mostly, they talked about how strange this was. We have the records. These days, this kind of storm may cause enormous economic damage to an economy that's used to communication and electronics and spaceborne technology, but it was our first realization that these CMEs could have a serious effect on Earth. And they're still the subject of continuing study. I want to mention briefly, for example, work by Jenny O'Kane at University College London's Mullard Space Science Laboratory, where she's been looking at stealth coronal mass ejections. You can see one here in this image, but using Solar Orbiter and Parker, finding these things coming from the quiet bits of the sun, but still packing a magnetic punch capable of affecting what we're seeing on Earth. When places like the Met Office make predictions of solar weather, they have to worry about these sort of things as well. And the further you get and the deeper you get into the literature, the more you realize that A, solar physicists are having fun, and B, these things are complicated. There's been great excitement, and these are real images stitched together. These are from Solar Orbiter, though they're showing a feature that Parker also sees of a switchback. So you can see this is a streamer coming out from the corona, and hopefully you can see there's a kind of S shape there. So normal theory would suggest that these things should just stream out, but that we keep seeing these changes. And it's to do with the twisting and alteration of the magnetic field of the sun in ways that we're only now beginning to understand from these missions. And I realize as I'm talking like this that we've come a long way from my piece of paper that said the sun was massive and hot. You realize that to understand the sun, because we have the ability to study it in detail, you have this complex magnetohydrodynamical puzzle that requires equations and computer simulations and sophisticated technology just to answer the question, what will the sun be like tomorrow? Let alone what will the sun be like in a decade or 100 or 1,000 years' time. It is a complicated system worth studying. And just in the last month, there's been the release of what's called the Decadal Study in the US. This is a National Academy report that reviewed all of heliospheric science and said what we should do in the future to study the sun. And they proposed a couple of missions, one called Lynx, which would have 6 spacecraft in Earth orbit, swinging out to 9 times the radius of the Earth to understand this interaction between the Earth and sun. But they're also proposing a polar orbiter to go for only the second time. You send a spacecraft out to Jupiter, you swing around Jupiter, and you swing up and over the poles of the sun, a region that we've studied once and have no pictures of, but which is crucial in understanding these magnetic interactions. One final question is that given that we can study the sun because it's close, it's important, I think, to think about whether the things that we see here must also happen on other stars. After all, we know the sun is special because it has us going around it. And so it may be that the sun has phenomena that we don't see elsewhere. We've seen star spots on other stars, mostly on large stars where we're able to resolve them. But one particular exciting line of inquiry that I think is fascinating and will be important in the next couple of years is the search for solar siblings, for stars that formed 5 billion years ago in the same nebula, the same nursery, as our own sun. We found one good one so far. It's called HD 162826. It's here in the sky, just in the summer sky from the UK. And we know it's our sibling based on how it's moving through the galaxy and also the amount of rare elements like barium that it's got in its atmosphere that matches the sun. It doesn't, by the way, as far as we know, have any planets. But amongst the 100 billion or so stars in the Milky Way, there are probably at least 1,000 others that were born at the same time as the sun. And a European spacecraft called Gaia has been mapping the nearest 2 billion stars, partly in the hope of finding these. I wanted to mention it today, partly because it's the subject of next month's lecture, which you should all come to, but also because Gaia ended an 11-year mission of mapping the sky about an hour ago. And so I've got a month to read up on 11 years worth of observing the sky. But one of the things it was built to do was to find our solar siblings and find out if the sun is unusual. I want to leave you with one final perspective. I've talked about Parker that flew as close as possible to the sun, but I also mentioned that we have these spacecraft, Voyager 1 and Voyager 2, out on the edge of the solar system, and they're carrying out scientific observations using equipment that's running on a shoestring. They don't have much power left, but they're able to monitor the unusual environment they found themselves in, because both of the Voyagers seem to have passed through what's called the heliopause, the region on the edge of the solar system where the sun's influence ceases to be dominant. And these spacecraft are now sailing through the galaxy, exposed to the interstellar environment. They still feel the sun's influence, but they're also out in the big wide world. But this was a source of frustration for most of a decade because NASA kept saying that the Voyagers were about to cross the heliopause. It wasn't clear whether they had done. One day it would look like they were in interstellar space, the other they'd be back firmly within the solar environment. And what we've realized is that this edge of the solar system, drawn in this lovely artist's impression as a nice smooth bubble, is actually a complicated place. Of course it's complicated. It's made by the sun, which you know is complex, but also because it's built up by these coronal mass ejections and this material that storms out through the solar system in a deeply nonlinear fashion. And so what happens on the edge of the solar system, way beyond Neptune and Pluto, which is not a planet, but out on the outer edges of the solar system, what you get is a build-up of bubbles sent from the sun via these violent processes that we're only now able to understand, creating a complex border which we've just managed to send 2 craft sailing through to explore. Between them and the thing moving faster than anything else, we're slowly getting to the point where we actually understand the true complexity of our star. Thank you very much.